Hello, I will continue talking about deep learning, and in this video, how we can use gradient descent to minimize the error function. We saw in previous video that we have a problem with discontinuities in the sine function. In order to solve this problem, we need a different activation function. There are lots of choices, and I will use two of them, logistic sigmoid function and the hyperbolic tangent or tan h function. These functions, as you can see in the curve, has S-shaped functions and they are continuous function. The blue one represents the tan h and the orange is the sigmoid function. Tan h ranges between -1 and +1, the output of it, and the sigmoid function, the output is between 0 and 1. In this slide, this is the mathematical definitions. You can ignore them, just focus on the shape and the graphical representation of the functions. And these are the formula of the derivative of the function. One thing to note that we can derive the derivatives of the function from the function itself. So we don't need actually the x explicitly. We just do the f of x. As you can see here, the derivative of tan h is the squared of the tan h function, subtract from 1. Let me describe that with a very simple neural network. We have a single neuron in each of two layers. We have neuron G in the hidden layer and F in the output layer. G will use the tan h activation function and F use the logistic sigmoid function. You will understand more in the future slides. We have stated the mathematical function for the entire network here. This function no longer includes any discontinuities. And the figure here ends with the symbol E, which is the error, represent the error function, which computes the square difference between the output of the network and the ground truth. If we now want to train the network, we want to minimize the error function. We will do that using gradient descent, and we will use mean square error as the error function. Therefore, the overall function that we want to minimize, we can get that by inserting the network function instead of y hat into the error. So this is the function that we need to minimize it using gradient descent. If we minimize the error, that means the function output is very close to the desired output for the given constant input example x. But how can we compute these derivatives? So we have the weights, WGF0, this is the bias weight, we have W1, W2, all of these weights. How can we compute these derivatives? Well, we will use the function composition and the chain rule of calculus. Let me revisit this by typical using example. If we have two functions, fx and gfx, we can create a composite function hx equals f of g of x. We can look at one neuron as function g of x. Each output is then used as input to the next neuron f of x. So we have f of g of x, where g of x is the neuron in the hidden layer and the outer function f of x is the output neuron in the next layer. Now that we have introduced function composition, let's discuss what the derivative of a composite function is. The derivative of f of g of x is f prime f prime g of x times g prime x. To make it more clear, let's give an example. We have the composite function hx equals 3x plus 4 squared. We can write this as inner function g, and equals 3x plus 4, and the outer function equals x squared. The derivative h prime is now 2 times 3x plus 4. That is the outer derivative times 3 is the inner derivative. This is the inner function, 3x plus 4. Let's assume that h with 3 arguments, x1, x2, x3, and it's a composite function, f and g. F has 2 arguments, x3 and g has 2 arguments. So the f function has 2 arguments, which is x3 and the output of the g function. The partial derivative of h with respect to x1 and x2 can be computed with the chain rule. However, the partial derivative of h with respect to x3 does not need the chain rule because x1 and x2 will be considered constant in that case. H is directly a function of x3 and not a composite function. We will see example of this later. We will now introduce a different notation to make it more readable when we work with multiple functions. For function partial derivatives, we will use Leibniz notation. I found it intuitive because it shows directly the dependency between variables. Assume that we have a variable z, which is set to the function f, and f is a function of variable y. Variable y in turn is a function g, which is a function of x. That is z, a composite function of f and g. We can now write this derivative as dz dy dz dy equals dz dy times dy dx. This is the notation we will use for the chain rule going forward when we work with partial derivatives in neural networks. Now let's apply the function decomposition and the chain rule to our network function and error function. We will start with stating the error as a function of the weight values w. We have the input values x, which are constants for a given training example. We now want to adjust the weights in a way that minimizes the error function. We will do this using gradient descent, and we will find the sensitivity of the output with respect to each weight, and then we will adjust the weights that the error is the most sensitive to. The sensitivity is the same thing as the partial derivative. And in order to compute these partial derivatives, we first need to decompose the function into smaller blocks. We have our error function. We can see that the innermost expression, which is the sum wxg0 and wxg1 times x1 and wxg2 times x2. This sum is input to the tan function, and the tan function represents the activation function of neuron G. Let's call this weighted sum ZG. So we see that ZG corresponds to the weighted sum for neuron G, and it contains the two inputs, x1 and x2. ZG in turn is used as the input to the activation function for neuron G. So we have the G of ZG equals tan H ZG. We multiply that by the weight WGF1 and add the bias weight WGF0 to arrive at ZF. This is the weighted sum that is the input to the activation function for neuron F. The output of neuron F is computed by taking the sigmoid function and using ZF input to that function. This is the network output. We now want to compare this to the desired value. We were gonna use the error function, the mean square error, which computes the square difference. So we take y minus f squared and then divided by 2, because we have two examples, x1 and x2. This is useful for computation thing. It makes the computation easier. This includes the error function, the activation function, and the weighted sum for both neurons. We are now ready to compute the partial derivatives of the error function with respect to each weight. We will get one partial derivative per weight. So the slide here show how we compute the partial derivative of the error function with respect to the weight WGF0, which is the bias weight for the neuron F. We state with this overall function. We note that all the weights except for WGF0 are treated as constant. That implies that both functions g and zg are no longer functions of any variables because all their input variables are constant. Therefore, we only have 3 functions overall for this expression. So we have the error as a composed function of e, f, and zf. The expression for the partial derivative with respect to WGF0 is dE dF times dF dzf times dzf dWGF0. This is using Leibniz notation. We can use the same methodology for computing all partial derivatives. The first partial derivative on this slide is the same as we computed on the previous slide. The second one is very similar, but it's computed with respect to weight WGF1. For the 3 remaining derivatives, g and zg are no longer constants, and that adds a couple of more factors. There are some observations we can make and by looking at these partial derivatives. Let's see. First of all, there are a lot of common sub-expressions here between all of these derivatives. This means that we can reuse parts of the computations and we don't need to compute each partial derivative from scratch. We will make use of that in the backpropagation algorithm in the next video. As you can see here, we can also see that each partial derivative is computed by walking the network backward. As you can see here, we multiply the error function derivative by the derivative of the activation function, by the derivative of the weighted sum, and by the derivative of the next neuron, and so on. More details about this will be shown in the next video. So all in all, backpropagation means we are training a neural network. Normally, in backpropagation, training a neural network, PyTorch does 2 things. Forward pass, compute outputs layer by layer and store all the intermediate activations in memory. Backward pass, use those saved activations to compute gradients. And I will talk about backward pass in the next video.